Hey everyone, so today we're going to work on integration by long division and completing the square. So the first thing we're going to talk about is completing the square, and this comes up when we are talking about these guys, aka integrals that end up being arctangent, arcsine, and arcsecant. These three that we have to know. Remember, these are in our top 15 integrals. So just as a reminder, when you guys are looking at this, a is a real number, and u is that variable expression, whether it be x squared, etc. So variable expression. Okay. And same thing, obviously, throughout. So arctangent, arcsine, arcsecant. Remember, that can also be written as inverse tangent, okay, or inverse sine. That's exactly the same thing. Okay, so let's do some quick examples here. Okay, so if we're taking the integral of 5 over x squared plus 16 dx, you can kind of just move the 5 to the front. 1 over x squared plus 16. We see this format. We have, not x, u is x, a is 4. Okay, so just refer back. You notice it's in that same pattern. So you say, oh, okay, this is the same as 1 over a arctangent of u over a plus c. And sorry, I forgot the 5, of course. You can just leave the 5 out front. And that's it. You could write it as 5/4 if you want. All right, so the next one, arcsine, you're looking for that number squared minus a variable expression squared. Again, feel free to move the -7 out to the front. 1 over the square root of 9 minus x squared dx. So a here would be 3, and u would be x from right there. And that format is arcsine of u over a plus c. And again, classic, forgot the -7. Sorry about that. Keep forgetting it. All right, there we go. So if there's a constant, it kind of just hangs out up front. All right, and the last one to look at, this arcsecant one, a little more complicated, but you'll see it will have u and u squared, or whatever that variable expression is, in this case x and x squared. And 81 would be that a squared. So a is 9, and 3, again, I'll just leave in front. I won't forget this time. 3 times, all right, here we go. 1 over a arcsecant of the absolute value of u over a plus c. And again, you could write that as 1/3 if you want in front, 3 times 1/9. Okay, so now what happens when we cannot factor, or when it's pretty close to being this, but it's not exactly? We're going to do something called completing the square. I really like this lesson because completing the square and long division are both exciting flashbacks to Algebra 2. So if you've been missing Algebra 2, here's your moment to shine. So what we want to do is get this to look like this, right, of some sort. Like we can see it's kind of there, but not exactly, because we have this whole thing sitting around. It's not a perfect square. There's an x there. So if you forgot what completing the square is, basically it's taking this expression, x squared plus 6x plus something, leave the 10 there, we can't just get rid of it. If we add something, we have to subtract that same thing to balance it. Okay, so what you want to add is this number divided by 2 squared, b over 2 squared. This is like a, b, and c if you were doing quadratic formula. 6 over 2 squared is 9, and that means I also have to subtract 9. Okay, so reason I'm doing this is because now if I take this part right here, I created a perfect square trinomial, and that means what multiplies to 9 and adds to 6, x plus 3 and x plus 3. So I wanted to create it to be this perfect square, aka 2 of the same parentheses. Plus 10 minus 9 would just give me plus 1. So now what I've got, if I rewrote this, would be x plus 3 squared plus 1 dx. And it's a little more clear now, hopefully. This would be u, and then square root of 1 is 1. Okay, so if we were to follow, again, we're looking for which one it matches. Hopefully you guys see arctangent, that first one. So 1 over a arctangent of u over a plus c. And you can kind of rewrite that a little nicer since we don't need that over 1. And that's it. So again, what we're utilizing is completing the square, okay, in order to get this to be a perfect square plus a perfect square. So The next one, you see a square root. If you take a look, square root is either going to be arcsine or arcsecant, but you'll notice there's not an extra variable out here. So we're going to be looking at arcsine, this guy right here. We notice again that this is not really ready to go. So we're going to have to do completing the square. So you can rewrite it. So we have negative x squared plus 4x, and we want to add something and then subtract something to get this to be a perfect square trinomial. If you have a negative out front, if you remember from algebra 2, we always want to factor that out. So it'd be negative x squared, factoring it out, minus 4x. We still can just say we're adding, okay? When we subtract, we're going to have to be careful. So I'll show you what I mean here. So again, what's going in this little space right here would be this number, negative 4, divided by 2 squared. So it's always b over 2 squared. And that number is 4. Okay, what did I really add though? I have negative 4, so I really added a negative 4. Okay, meaning I have to subtract a negative 4. So let's see what I have here, guys. I've got negative, what multiplies to positive 4 and adds to negative 4. That'd be x minus 2 squared. And then I have plus 4. Even though this looks a little bit strange, it actually fits in really nicely, because if you rewrite this, we have integral of 1 over the square root. You could kind of switch the order here as long as you keep the signs. And you'll notice that exactly matches a squared minus u squared. So a would be 2, u would be x minus 2. And again, this formula would be arcsine of u over a plus c. All right. So that's it. We're going to try one more. You guessed it. It's going to be arcsecant. Reason I can recognize that it's arcsecant is I have a variable outside, and then I also have variable in a square root. So it kind of is looking like that u times the square root of u squared minus a squared. But this is not in that format, so I'm going to take it and complete the square. Plus something, plus 5 is just hanging out, and then I'm going to have to subtract that thing I add in. I take this middle number, divide by 2 and square it. Negative 6 over 2 squared is 9. That means I also have to subtract 9. I take this whole piece here, and what multiplies to 9 and adds to negative 6, that would be x minus 3, x minus 3. Plus 5 minus 9 is negative 4. So, and this matches up really nicely. You guys can see that u is going to be x minus 3. So 1 over x minus 3 times the square root of x minus 3 squared minus 4. And if at any time you want to take a look up at the 3 equations, that's always a nice thing to match up. So we'll notice we have u, and then u squared, u squared, and then we have a squared. So u would be x minus 3, a would be 2, and our formula is 1 over a arcsecant of u over a plus c. All right, so we're done with those. That, again, is integrating using completing the square, and that comes up when we use those 3 inverse trig integrals. Last thing we're going to talk about, 2 more problems, integration by long division. Okay, so basically what you want to do when you approach a problem like this, and again, we're just doing different types of integration, right? We've done u sub, we've done kind of, or just anti-chain rule, if you want to call it that. We've now talked about using completing the square, sorry. So one more thing we want to talk about is what if we run into a problem like this? Okay, the first thing you want to try to do is algebraic manipulation. What I mean by that is, like, if you had a problem that looked like this, okay, the first thing I hope you guys would do is try to factor, cancel, and then we just have to do this, which would be, x squared over 2 plus 2x plus c. This is a nice format for us to use. But if it's something we can't factor, such as 1 and 2 below here, either we can factor it and it doesn't cancel, or whatever may happen, but we have this kind of division of polynomials. And also u sub doesn't work. So if you take a look here, u sub doesn't work because, first of all, even if this was like 8x plus 5, this x plus 2 isn't going to match up, and it's in the denominator, which is kind of strange. So long story short, this is where long division comes in. You tried factoring, u sub isn't going to work here, so let's do some long division. And again, this is going to be a fun flashback to Algebra 2 The best days of your lives. Let's do it. So we put x plus 2 on the outside. 4x squared plus 5x minus 10. If you remember synthetic division, you're also welcome to use that if the factor in the denominator is linear, meaning it's x to the first power. If it's not linear, we can't use synthetic division, hence why I'm showing you long division. So how do we do this? Well, the first thing you want to do is get something that says 4x squared right here. You want it to exactly match up. So what would you multiply x by to get 4x squared? Well, I'd multiply by 4x. 4x times x is 4x squared. 4x times 2 is 8x. I write that down. I am now going to subtract both pieces. So subtract, subtract. 4x squared minus 4x squared is 0x squared. 5x minus 8x is negative 3x. I bring down the negative 10. Okay. If this doesn't cancel, you did it wrong and start over. So you want it to be exactly the same. So we're going to do that same thing now. How do I get negative 3x? What would I multiply x by? By negative 3. So now I'm going to take negative 3, multiply it, negative 3x, and negative 6. Negative 3 times 2. I put a line. I get a new color if you want. You're going to subtract, subtract, aka change both of the signs. Cancels, needs to cancel, or you have to fix it, and I get negative 4. Okay, so negative 4 does not go into x. This is your remainder. So if you rewrite this, you write negative 4 over the divisor. Okay, so let's rewrite that here, guys. We've got 4x minus 3 minus 4 over x plus 2 dx. This is the same thing, right? This is dividing these two polynomials. Here's what I got. It wasn't perfect. There was a remainder, but now we can take the antiderivative because we know how to do each of these pieces. So 4x, well, raise the power, divide by the new power. 3x to the 0th would be 3x to the first divided by 1. And 4 over linear x plus 2, remember that would be natural log, since this is x plus 2 to the negative first, technically. If I add a power, I'd go to 0, divide by 0. I know this is a special case, therefore, natural log, absolute value, x plus 2 plus c, and that's it. So even though we weren't able to factor and cancel anything out, we still were able to successfully take the antiderivative here using long division. Again, this comes up when we're using a polynomial over a polynomial. Okay, so let's try out x squared plus 9 over x minus 4. You try factoring, it doesn't work. We can't factor x squared plus 9, so we're going to use long division. Okay, x squared plus 0x plus 9. So if you're ever missing a term, you want to add in a 0x or 0x squared, whatever's missing. It's going to be a nice placeholder, and it will make more sense once we finish up here. So x times what is x squared? Times x squared minus 4x. Take a new color, subtract, subtract, needs to cancel, and now I have 0 plus 4 is 4x. So now you'll see why the 0 was helpful. 9 plus 4x wouldn't have really gone together, right? They're not like terms. Plus 9. 4 times x, right? So I multiply by 4x minus 16. Common mistake is people forget to subtract both terms. We end up with 25. So plus 25 over whatever you divided by. So take this integral, I'll move down here. I have x plus 4 plus 25 over x minus 4. You guys will notice this almost all the time is natural log, right? Because it's the divisor. It's the divisor in the denominator, excuse me. That's a linear factor. So typically this is going to be natural log, that last term. Add a power, divide by the new power. Add a power, divide by the new power. Plus 25, natural log, absolute value of x minus 4 plus c. And that is it. All right, well, thank you so much for watching, and please let me know if you have any questions.